All right. So for well, you can no, I'll do this one. Okay, so welcome to class. We are last class period. What we did, review. Last class period, what we did was we talked about integrated rate law, and we did integrated rate law is the calculus derived understanding to produce a linear equation for identifying whether we have first, second, or we have this unique zero order, which often is pseudo order under very specific conditions for a very limited time. Very unlikely that you will actually be questioned on it, to be honest. Pseudo order would most likely not be questioned. I am trying to get this up on the screen. But that's where we left off. And I don't know why my thing is not picking up screen mirroring. So give me a second. Okay, so that's kind of where we left off. And then we also introduced at the end a very specific type of first order reaction, which was half-life. And half-life, the big idea behind half-life that you're expected to understand is, can you use the equation given on the equation sheet where you relate half-life and the rate? Could you do the 1/2 raised to the power of how many half-lives to predict how much concentration is left of the original, what fraction of concentration is left? And then finally, could you recognize, okay, that half-life is a first order integrated reaction rate and plug it in to the provided integrated derived, okay, reaction rate laws that are linearized, okay? So these practice problems, I didn't really feel like going over one because that's just a lot of calculator pushing and graphing. I assume that you are fine. And nothing on the AP would actually ask you to really graph diligently. They might ask you to graph within a certain range of correctness, but that particularly applies to Unit 8 titration curves, which you're not at yet. But so graphing isn't a real skill tested in AP. It's more extrapolation of graphs, okay, or modifications. So that's why I skipped over practice problem 1. But practice problem 2, what we're told is that the rate constant of a first order reaction is 4.03 times 10 to the negative 3 seconds to the negative 1. What's the concentration of reactant remaining after 74.6 seconds, assuming initial concentration is 0.3? So what you guys should have done is you should have used your natural log integrated first order. So natural log of C final equals negative KT in seconds. Time here is always assumed to be in seconds, plus natural log, please tell me it's plus. I'm going off of memory here. Plus natural log of, thank you, original. So this was a plug and chug. Like these are your dream problems, okay? So you get reaction rate or rate constant, sorry, is negative 4.03 times 10 to the negative 3 seconds to the negative 1 times time, which is 74.6 seconds. One reason you know time has to be in seconds, by the way, is because rate law constant is in seconds. And your goal is to cancel out the units to have molarity left, okay? Plus the natural log of the initial, which is 0.300. And you can stick the molarity in there as a unit to kind of remind yourself. Honestly, unit tracking in these problems with ln is a little weird. Just kind of know that you have to end up in molarity if you're going to do concentration. And what did you guys get for your value after you take the raised to the e, not the anti-natural log, but raised to the e power? What did you get for the final concentration? 0.222 molarity to the correct sig figs. Excellent. Problem 3, reaction 2B goes to C and A, is a second order reaction with the rate constant of the following. And if the initial concentration of B is this, a singular reactant, what is the concentration of B after 45 minutes? So what is 45 minutes in seconds? Oh, that's nice. Okay, yeah. No, I guess you don't. That's really nice, actually. Yeah. So then you just do second order is CF. No, it's 1/C. Guys, I'm going off memory. Equals 1/C equals positive KT plus 1/C initial. Am I doing this off of memory correctly? Okay. So then you get, what's the concentration of B after K? Equals K, which is 0.15 molarities to the -1, because it's liters over moles, which is the inverse of molarity, times minutes to the -1. K times the time, which is 45 minutes, which great catch. Thank you, Annalise. And plus 1 over the initial concentration, which is 2 molar. Oh, way too many sig figs. Gee willikers. And what'd you get for your final concentration value? And it is a 2 sig fig number, so it should be 0.30 molarity. But look at the molarity rate, or sorry, the rate constant, it's 0.15. And 45 minutes. So 2 sig figs. We don't need to go over problem 4. If you want a pseudo reaction just to know how to plug and chug into the pseudo reaction integrated rate law, you're welcome to. Again, 0 reaction orders are very rarely tested or quizzed on because they're just so uncommon anyway. All right. You should know they exist. You should know that they're under limited conditions, limited time, and that concentration is not an affecting factor of the rate change, but that's about it. I highly doubt you would have a 0 order rate law. Okay. So, any questions regarding that? All right, perfect. So yesterday you guys watched a really quick short video on chemical energy, because now we're taking a look into how do we understand the mechanism of a chemical reaction, which reveals, by the way, our understanding of the rate, because the mechanism, the way that it goes through collision, tells us how effective and likely and fast it will do the reaction. So we're going to take a look now through the lens of energy. That's where we're headed. So you guys learned about chemical energy. You learned about enthalpy, which is like the fancy term for chemical heat. Okay, essentially heat in a reaction. Enthalpy is just a fancy way of saying heat in the terms of chemistry processes. Okay, and so you learned about 2 categories, endothermic and exothermic. Can you explain to me at a particulate level why we see exothermic or endothermic reactions, comparing bond breaking versus bond forming? What is an endothermic reaction?
In an endothermic reaction, the energy needed to break the bonds is greater than the energy formed by making new bonds.
Excellent. So remember, anytime you break anything, you have to input energy. If I were to smash, like I did this this clipboard, I got excited and I smashed it down. I inputted energy. It broke. But let's say it reformed something new. It didn't. But let's say I smashed it into a million pieces, and then like those cool Matrix movies, they all fly together into something new. Okay. The idea is then you theoretically release energy, because it's whenever you bond, you're stabilizing. If you're stabilizing, you're going to a lower potential energy. If you're going to a lower potential energy, you're theoretically releasing energy from the initial strain of inputting energy. Yes.
You actually smash that against something?
Yeah, the table.
Right.
I just got excited. I'm a lot stronger than I look. I could throw a mean punch. So, okay. So, excellent, Liam. Thank you. So, bond breaking, always input of energy. Bond forming, making product, new bond arrangement, always release. If my overall net energy change is positive, I'm endothermic. That means overall, my new arrangement is at a slightly higher energy than my old arrangement. But then the question is like, why do we even make it then? Okay, well, it's because it goes through this really interesting middle step called activation, or the activation energy, aka the formation of the activated complex, which is the weird configuration of breaking and forming at the same time that you have to think about as like the formation of wringing a chicken's neck. Okay, it's like high tension, high strain. Have you ever tried to kill a chicken by your hands, or a bird? What you do is you take the I used to be a horseback rider and the pigeons made too many babies. So we had to get rid of them. So what you do is, I didn't do it personally, the dads would. You go around, because we didn't have a knife, and it's worse to be blunt, right? To do a blunt knife. That's why the guillotine was actually a gift. It was effective as long as they sharpened the blade beforehand. But we didn't have that. Okay. And we won't just go into a chemical bond and just like slice and dice it like Fruit Ninja. So what you have to do is you have to, okay, you have to think about when the collision happens, it has to be enough force that it contorts the bonds, the old bonds, causing a high potential energy activated complex. It contorts it and snaps it. And at the same time, all of your desired particles are right there anyway. It immediately starts forming at the same time. But that's why endothermic reactions still exist, because the relative energy is still lower than that stage in the process. Even though you would think, well, why would I make a new formation that's technically higher energy than when I started? Well, throughout the process, it's still more favorable because you had to go through that huge hump. Now, a catalyst lowers that hump. It lowers the process, the mechanism of creating that chicken neck strain. High energy, high tension, high strain. Forever think about that. Okay, so then exothermic. Could someone describe the exothermic in terms of bond breaking and bond forming? I know the chicken thing is really violent, but it really... anyone want to explain exothermic? We all need to teach you how to raise chickens and do the deed. Do the deeds. Yeah.
So in an exothermic reaction, the energy required to break the old bonds is less than the energy released when forming new bonds.
Exothermic.
Exothermic, yes.
Flip it. What?
That sounded right. Yeah.
Say it one more time.
So the energy required to break the old bonds is less than the energy released by making the new bonds.
Okay, yes. So the energy required to break the bonds, okay, is less than the amount of stabilizing energy required to, or as a product of forming and releasing. Excellent. Okay, perfect. So that's where we are. And then I also like went over some notation stuff. This is really just valuable for representing an actual quantitative value for tracking heat in a reaction that we can now use for unit conversions because it's a derived unit. So now we can quantitatively describe energy per mole of reaction according to the stoichiometry of the reaction via an exo and endothermic values. Okay, any questions regarding that? Activated complex, activated chicken. Activated complex.
I am never gonna go to the farm ever again.
So I'm gonna have now Keaton and Kevin take over for the potential energy diagram. It's really simple, and then I'll take over for and catalyst part 1, and I'll take over catalyst part 2, or you can take over catalyst part 2, and then I'll take over reaction mechanism. The goal is to be through this in about 15 to 20 here, so it's only 10 minutes of me. All right, boys, come on up.
Okay, so potential energy diagrams. The definition is a graphical illustration of potential energy changes that occur throughout a chemical reaction. And so while you're writing this down, there's sort of like 2 main reasons that we do this and that we look at these graphs. And you write slow. Okay, first is that you can easily see the change in H. And the second is that it shows the atomic rearrangement process according to energy. So once we get to that part, once Keaton's done writing, we'll see how that works. I'm what?
At least we can read.
No, it's good. It's just takes a while. Yeah, so the first reason is that it easily identifies the change in H, aka endothermic versus exothermic. And the second reason is that it shows the atomic rearrangement according to the energy process. Yes. Question about what something says? No? Yes? No? Okay. Okay. So anyways, going down to the graph. You see this. This is the reactants, and then the product is at the very end. And so the line that is given sort of shows the whole like change of the energy from the beginning to end. And so with this sort of reaction, is it endothermic or exothermic? Exothermic, yes, because the ending energy is lower than the beginning, right? And that's pretty easy to see. And that's one of the plus sides. And other thing to note here is that we can also see other things like the activation energy and change in H. So if you need like a formal equation for this, it would be tangent. No, it's here. Activation energy is the potential energy of the activated complex minus the potential energy of reactants.
Yeah, so one of the things that's important about this diagram is really that it shows the whole energy of everything in a chemical reaction. So you can see it's illustrated by the diagram at the very top. It has the activated complex. You can see that that is the highest energy state of the reaction. And you can see the activation energy pretty easily, which is just the difference between the reactants or the potential energy of the reactants and the activated complex. And then you can also see the enthalpy pretty easily because it's just the other side, which is the difference between the potential energy of the reactants and the products. And then this, yeah, it's just really easy to see from a glance everything you need to know about a reaction.
Yeah. And it's just pretty, yes. You go first. You already started talking.
In regards to why the activation energy to the final product is a slow curve rather than an immediate jump, because your activated complex seems to be an almost immediate process, like the snapping of a snap, when you experience an extreme drop of energy and then bubble out. Or
Well, in each molecule, it would be like instantaneous, but over the whole like if you have like a reaction taking place in a container, right? Not all the molecules react at the same exact instant. And so it takes a little bit of time for them all to go, which is why it's like more of a slope.
Shiri, do you have anything to add?
as in, why exactly isn't the activated complex creating an instantaneous drop in potential?
Because the idea, well, it's a relatively instantaneous because what you have to realize is that the scale of reaction progress is not accurate in terms of if you don't know how time, that could be a nanosecond, right? So it could look instantaneous if you zoomed out.
But relative to the other parts of the graph, as in heating up, would heating up take the same amount of time as you dropping? Because it seems
No,
like
because this isn't telling you directly anything about rate. Like this tells you nothing about the rate itself. Like nothing on the graph actually can be directly tied to like if my curve is bigger or shorter or longer or shifted left or right. It doesn't tell you actually anything about rate. What it does tell you that we can connect with rate is that the higher the activation energy, most likely the rate will be slower because it takes that fewer molecules are successful. That's the only thing you can directly connect to rate on this. But you can't connect time really to this.
You're also not seeing it heat up exactly. You're just seeing the reactants. Like that flat line at the left is the kinetic energy of the reactant. And then that increase in kinetic energy is like when they're breaking apart.
Potential energy,
Potential energy.
It's all about positioning of the molecules.
wait, so just to be fair, that rising up to the activation energy, is that a process that some external force is applying the energy, or is
No,
that
it's-
kind of-
When the
the-
atoms are colliding.
It's the initial, yeah, coming together,
Bonds are-
positioning.
Also, it's not really a physics way of understanding potential energy. It's
Yeah.
not really, doesn't really have to do with movement it's more so like potential energy and chemical bonds is a little bit different in terms of like it can be affected by their position within a molecule or like their position in general, and not just like, it's up on a hill, it has potential energy.
Like what an activated complex is.
Yeah, that's what Miss Judy was talking about with the chicken's neck, but basically the idea is there's kind of a diagram right here in the notes, but the idea is like you have these two molecules and they're hitting each other, and it's not like you have two molecules and then they all of a sudden become two separate ones. The idea is you have two molecules, and for, I don't know, and it could be a nanosecond, they hit together and they're all just one big blob of every single molecule that's reacting. And then eventually when it twists and breaks apart, you end up with your two separate ones. But the idea is the activated complex is this period where everything is mashed together before it twists and breaks apart.
So it forms a compound that's unstable and becomes the bonds.
Something like that.
But it's not like it like becomes a completely new compound, like a new molecule.
It's not really a molecule when it's in the activated complex. It's kind of
It is
just,
a transitionary complex. We actually use the symbol.
So it's not like a bonded molecule.
It's not a truly bonded molecule because it's both breaking and forming. It's bonding and unbonding at the same time. So it's kind of like saying
It's just getting mashed together.
it's getting mashed together. Like literally, like let's say Ava, get up. Ava, let's collide. Okay, so let's say Ava and I. Oh, actually, Ava needs to come with a partner. Maria, come with a partner. So
I'm
you're my
sorry,
partner.
what?
Maria. But, sorry,
Okay.
my little sister's name. I'm sorry.
Should I?
I'm sorry. So let's say this is being caught on video. Oh god, no. Okay, so let's say that your partners. Can I have a soul shit? Okay, so let's collide. So we come together as a partner. We're two molecules.
What are you doing, Ava?
We're two reactants, and in double displacement, I want to get with Ava, okay? And Maggie wants to get with Sasona now. So what happens is if we, okay, come and interact, what happens is as the bonds are breaking, let's break apart, grab kind of each other. What's happening is as the bonds are breaking, we're forming, and this, I guess you're actually gonna go with Ava because this is how it aligns better. And then we're the new bonds, okay? But that initial circle, kumbaya, this state where Ava and Maggie are starting to break, and me and Sasona are starting to break, but at the same time, Ava and Sasona are starting to make, and me and Maggie are starting to make our bond. That's the activated complex. And it's a high energy, high tension, because what's really happening is Maggie is holding on to dear life for Ava, and I'm holding on to dear life for Sasona. I'm like, don't leave me, okay? But we're both needy, and so Ava and Sasona being smart are like, no, I'm gonna go with the more relaxed coupling, and me and Maggie get coupled together. Got it?
That actually makes a lot of sense.
Thank you.
So in regards to this like process, when you have two compounds like colliding, are those the elements?
Are those the elements being what?
Like if I have like water and a bunch of chlorine, they collide. Those are the two compounds.
Yeah.
Mhm.
So in regards to the composition, is that the molecule colliding with itself, or
Yeah, it'd just be like the moment when the bonds start to break, I guess.
I know what uses it is.
Miss Judy.
I need to like, I need to feel the same. Because I forget how to use substitute, yes.
How about we can come back to this at the end, but let's just move on to right now.
solve for EA.
So yeah, and then going back, Mashidi talked about the Arrhenius equation briefly, which I don't know how important that really is, but she has to include it apparently.
What do I have to include?
The Arrhenius equation, but
Yes, I do.
it allows you to solve for activation energy, which I guess is nice if you don't get given a nice diagram such as like
Yep, pretty
this.
much.
Um,
So
now-
no need to walk them through the practice problem, just let them do it. Go for it.
Okay, Miss Judy did mention this briefly, and I'll mention it though. We have the symbol for the activated complex that looks like this, right? Oh,
Yep,
sorry.
it looks like a wire, like a Wi-Fi wire. What do you call those?
Telephone pole?
Thank you.
A Wi-Fi wire.
Wi-Fi wire?
Yeah.
no.
So we have
No,
the
literally, like,
Wi-Fi wire?
if I know what that is.
so we have the Wi-Fi wire
I
symbol.
communicate by pigeon.
The ones you killed.
They don't deliver it right, you know what I'm saying?
Anyway, so much for going fast through this, but we have this Wi-Fi wire symbol that denotes the activated complex. So that's what you're seeing if you see this on a graph of activation energy like this. So yeah, go ahead and try this problem.
Okay, can I get a volunteer for each of the 4 parts? Yes, one.
Endothermic.
It is endothermic.
That's the starting potential energy less than the ending potential.
Number 2.
The activation energy is 80 kilojoules per mole.
Number 3.
Central energy of the activated complex is 100 kilojoules per mole.
And last one, what is the change in H? 20 kilojoules. Yes. Very good. All right. Okay, so now moving on to reversible reactions. Just as the name implies, they're reactions except they're reversed. And so the definition is chemical reactions undergo specific conditions to go in reverse, basically undoing itself. And if we look at these graphs here, it's basically just flipped forward to backwards, right? And so the first one would be an exothermic, it start at higher and then you go to lower. And then if we flip it, not only does it become endothermic, but the activation energy is also higher, which is why it's like less favorable. Yes?
So is a reversible reaction considered equilibrium?
Yeah.
Okay.
Yeah. Equilibrium is going to be very, very important in units 7 and 8. So get excited for that. But the big idea here is that it's kind of this diagram right here, like this stuff is a little bit weird. I don't understand what exactly is trying to be shown, but you can see on the left, the forward direction, we're starting with our what looks to be some two diatomic elements. They hit each other. They're all connected to each other. This is the activated complex in the middle. And then eventually they separate and we're left with some new unknown compound. And then on the reverse side, we've started with our, our compound with 2 different elements, and they hit each other again. And we go back to our, I guess we'll call it diatomic state. And these reactions will usually be happening simultaneously, like a bunch of them at the same time. But the big idea here, and this will be important in unit 6, is that it's down below right here. As you can see, the distance between the potential energy of the reactants and the potential energy of the products remains the same, because that's just how distance works. But but the sign is going to flip. So the absolute value of the enthalpy is going to remain the same, but it's going to be the opposite. So when the reaction goes in the reverse direction, an exothermic reaction will become an endothermic reaction. And however, because the starting location or the starting potential energy of the reactants is changing, the activation energy for the reaction is going to change. It's pretty easy to see on the graph, because you can see that at least for the exothermic reaction, the potential energy of the products is higher. So we have there's less distance between it and the activated complex, aka less activation energy. And then when we flip it to be endothermic, there's more. So but as it says here in the blue, our little caveat is that the energy of the activated complex always remains the same. That's also kind of illustrated in our diagram. I don't know what the little lines are for, but you can see that in both cases that, and it's also rotated like 90 degrees, but the activated complex is the exact same in both situations, regardless of whether it goes forwards or backwards. So the activation of energy of the reaction remains the same, whether or not you flip it. You have a question, Alice?
So for a reaction to be reversible, that must be
What must be true?
the energy of the activated complex must remain.
I don't know if it must, well, I don't know. I don't think that's the defining characteristic of what makes a reaction reversible or not. But if a reaction is reversible, the activated complex will have the same potential energy going both directions.
You know why that is?
Miss Judy, feel free to expand on this, but I think it's just because regardless of which direction you're coming from, the activated complex ends up being the same.
Yeah.
Like you can see right here, this right here and this right here. It's rotated 90 degrees, but it's the same thing on both sides.
Reversible reactions are truly a thing of nature that we don't exactly know why certain reactions are reversible and what's not. We can create correlations and patterns, but there's just some reactions that are just like, no, I'm not gonna do it. It just, and part of it is favorability, which you're gonna learn in unit 7 and 9, is it's just not a favorable process to undo it. But there are some processes that are just like meh favorable. You're like, I can go either way. Hey,
Yeah. We have this practice problem for you guys, but question?
Could you have two reactions that both are reverses of each other and can exist in equilibrium without having the same activation complex?
No, I wouldn't imagine so, because if they're both of the same reaction, then that middle step is the same, right?
Or like, could you have a cycle of 3, for example, and then each of them has their own unique activation complex?
You're getting into elementary step reactions, but I'm gonna help you break down where we have a charge, molecular, reactive situation. I'm gonna explain that later.
Great.
Do we have time for them to try this? Or-
They can do it on their
It
own.
shouldn't
It's
take
fine.
you 2 minutes. Just go
Okay,
for
we'll
it.
give you a very brief amount of time to do this.
And
Shouldn't
then
take too long.
All right, so quickly. Get some volunteers. For number 1. No. Yes. Yes. Forwards because
If you go this way, then the potential energy will decrease.
yeah.
What is the enthalpy for the forward reaction? And what is it forward or reverse? Exactly.
Yeah. Okay, what is the activation energy for the forward and reverse? For the full. Yeah. And the potential energy for the activated complex is what?
50 joules per mole.
Forwards and backwards, right?
Notice the I wrote this on the endo, on the cycle. Activation energy stays the same. We call enthalpy a state function reaction, because the final and initial state are all that matter. That's just some terminology for you. Enthalpy is often called a state function reaction because only the final and initial matter, but understanding the mechanism of activation energy matters, and that's kind of a different subcategory.
Yeah. And now our last sort of small topic is about catalysts. And so if you've ever taken like AP Bio or some other class, you've probably heard of what a catalyst does. And it's a chemical species that changes the pathway of a reaction to decrease the activation energy by decreasing the energy of the activated complex. And how it does this is by providing an alternate route. And so for a lot of catalysts, one of the defining features is that they're regenerated in the reaction that they're used for. And so this is like, you've gone over a two-step reaction, or like multiple step reactions, right?
No.
Oh, well, sometimes you have like multiple smaller reactions that take place in a bigger reaction. And so the catalyst helps that first sort of reaction get started. And so it lowers that activation energy. And then, so it's used up there. And then later on, it's like sort of made back as a product of a later step.
So the idea is some reactions are so complex that it's easier to achieve them in chunks versus one go. And what we see is that between the individual reaction steps, what we're going to talk about next is elementary reactions, you'll see that catalysts are best identified as a chemical species that is added and consumed temporarily, but then produced at the end, so that overall net reaction-wise, they are not actually part of the reaction. Net reaction-wise, they don't actually get involved in the reaction. What we do at most is write them above the arrow as a condition. We almost treat catalyst like a condition. That is, like, instead of saying 25 degrees Celsius, I added plutonium and catalyst.
Problems like the Frank reaction is in the presence of H2 gas.
And catalysts are guaranteed increase in rate of reactions, hands down.
Do catalysts correspond to the reactions in terms of like a heat efficiency, just like add catalyst to end reaction?
I mean, there are some catalysts that just don't work for a reaction, but most of them do. Like, there's just kind of like a subsect of catalysts, and that's what I'm gonna talk about in a second once they go through this problem with you guys. Go ahead and try out the practice problem for a second.
And can we say,
But is one catalyst better for a certain type of reaction?
Yeah, sure, yeah.
Okay.
and a catalyst is the only way that you change the energy of the activated complex?
Yes.
Right?
It's the only way that you actually change the pathway. Every other way, you're increasing the molecules portion of making the reaction happen. Go ahead and try that practice problem, guys. Right, we should be done by now.
All right, let's go over it. A, what is the reaction endothermic or exothermic? Exothermic, because the change in H is negative. B, what is the activation energy for the catalyzed pathway?
25 kilojoules.
25
The catalyzed
kilojoules.
pathway.
No, the catalyzed is 10 kilojoules.
Mhm. And then 25. What is the change in H for this reaction, and how does this value change with the catalyst?
Someone, what is delta H?
Oh, the activation.
Mhm.
Remember, catalysts only affect the activation energy. It does not affect the final and initial, and enthalpy is all about final and initial.
And how much lower is the potential energy of the activated complex with the catalyst?
15 kilojoules per mole.
15 kilojoules per mole. How does this affect the reaction rate?
Speeds it up.
Speeds it up. Yeah.
More percent of particles are able to meet that reduced requirement, activation energy.
Did you find it?
Great. Going over the types of reactions. Again, this is something I tried to get rid of, but the AP does specifically request you to know these types, but I have yet to see a
You got
single
this,
question.
bro. You got this.
So we're gonna go over it super briefly.
So basically, now you're not liable for saying that.
It's on the AP course plan. Like, they ask that you know the types, and I have not seen a question at all about them.
Do I need to write anything down about this?
Just write the general idea. So heterogeneous.
You wanna type it?
Catalyst. These are, you can categorize catalysts by types, which is kind of question. Do specific catalysts just work with specific things? Kind of, yeah. So
I think you should explain this. I think you should explain this. I don't know what's going on.
So heterogeneous catalyst. You can write. Heterogeneous catalyst is where the reaction is limited to surface area, and usually involves solid state. So we often use a heterogeneous catalyst when we have limited surface area and solid state chemicals, or chemicals in the solid state. Homogeneous catalysts are when the catalyst is the same phase as the reaction. Same phase of matter as reaction system. Catalyst is same phase of matter as reaction system. Binding catalyst. This is the most common when we think about biology. Binding catalysts are where you see biology come into place. What happens is the catalyst binds with the reactants to assist with favorable positioning. So you kind of hold down your reactant particles. You're like, you must collide. And specifically in this orientation. To assist with favorable positioning. So enzymes are biological binding catalysts. Temporary covalent catalysts, okay, they involve actually bonding with reactants. This is where you actually create what we call an intermediate or a transitionary complex. They actually bond with the reactants, creating an intermediate or transitionary complex. Chemistry, we tend to work with temporary covalent catalysts a lot. So when in my research, we added a catalyst, it created this intermediate that was like real gray. But it was consumed so fast, and if you let the reaction sit overnight for like 8 hours, you wouldn't find it again. It would be regenerated. We could totally purify it. It was fine. No big deal. Surface catalysis. This is a type of catalysis in general where we see a temporary covalent bond formed with a surface. Temporary covalent bond formed with a surface. Again, actually, that's where for you guys in the future, and for my previous AP students, that is H2 hydrogenation, catalyzed hydrogenation. You form a temporary covalent bond with your platinum surface that speeds up the reaction. For those of you that have no idea what's going on, you will. All right. I believe it's my turn now to move on to elementary reactions, addressing a Lopes question. What if we have multiple molecules combining, right? So, thanks, boys.
Can you go back up so I can copy that on?
Okay, let's do this. Could you take the stool back? All right, we all good here? All right, so now that we kind of understand the role of energy in understanding and tracking a chemical process, what we need to consider is, what does this mean for complex reactions that involve 2 to 3 molecules colliding? How do we make that easier? Is there a way to make it easier? And what's the role of activation energy in the process, in this idea of temporary configurations or compounds being formed? So there's a really important idea that we need to study, which is reaction mechanisms, and particularly elementary steps within reaction mechanisms. So a reaction mechanism, when we look at a reaction mechanism or the way that a reaction occurs, what you have to realize is that most reactions actually occur through many steps. Because if you think about colliding 3 things at once in the right positioning at the right force, like that's a lot of effort. Have you ever been with your friends and you try to pick a movie and it's like 40 minutes later, you still haven't picked the movie, right? Trying to sync up. It's a lot, and it gets worse the more people there are, right? It's the same idea. Like it's just not going to happen. So isn't it nicer if you could break down into maybe 2 people go and watch a film and the other 2, right? Same idea. So what we do is most reactions go through many steps, and particularly we call it a sequential series. A sequential series of reactions. So things that you want to consider that are often part of understanding a reaction mechanism and the sequential series that make it up is that you often have what we call relative reactants. So a reactant in one of the steps might be the next product, right? Or sorry, actually a better way to put it, a product in one step might be the next reactant in the next step, okay? We get relative products. We get perhaps a catalyst. Remember, it's regenerated, and it's Kevin was hinting at earlier. You can often spot catalysts easier when you break down into these individual steps because you see it consumed and then reproduced in another step. And then finally, intermediates. These temporary reaction combinations that create a temporary bond that is then broken down later, right? So a product that is then consumed as a reactant in the next step that doesn't show up in the overall net equation. Okay.
Pretty common MCQ.
Hmm?
Pretty common multiple choice.
It is a common multiple choice. This is a really common multiple choice. So again, why multi-step? So it's just easier, okay? Slash increases percent of successful collision.
I don't know about the movie thing, but one thing I kind of thought of was like, imagine you have two other friends and you all have like, I don't know, basketballs with Velcro on them or something like that, and you're trying to throw them and have all three hit each other at the same time and stick together. Like, it's not really going to work that easily. I mean, a lot of you probably would have a hard time throwing two basketballs and getting them to stick together, but it would be a lot
Can't even
easier to
throw
throw
one.
two and try and have them hit each other and then throw a third one and try and have them hit the three rather than try and like have three things collide with each other all at the same time and hope that it's going to work out.
And at the perfect position, right?
Give
Um,
me the demonstration. I
I used to be a cheerleader, the flyer. If someone could basket toss me and catch me, guaranteed. So thanks. So why multi-step? It's easier. It increases the percent of successful collision by simplifying mechanism into multiple steps. Okay. So that is what we call an elementary reaction. It is the an individual step in a more complex reaction series. So a couple of things to know about elementary steps is that we do balance individual elementary reactions. Two, the reaction intermediates, those that are produced and then consumed, the ones that are produced and then consumed pretty much sequentially right after, produced and then consumed, are easily identifiable. Okay. C, we usually only describe reaction and collision between 1 to 2 particles. So elementary steps simplify into 1 to 2 particle collision reactions. D, the sum total of elementary steps should equal your overall reaction, which means, of course, no catalyst, no intermediates. So that means the overall, your catalysts and intermediates should cancel out. E, the rate law, the overall rate law. Why? What is that? What is that? The overall rate law of your reaction is determined by English is determined by the slowest individual reaction rate law. So it's kind of like saying that you're only as strong as your weakest team member. You're only as fast as your slowest member. Yeah. Where's the track people when I need them? It's the bottleneck. Exactly. It's the gatekeeper, the slowest individual reaction rate. So some terminology, oftentimes what you'll see referenced in an AP problem is they use this terminology on molecularity, which is basically a way to describe how many particles are involved in a reaction collision. So to be unimolecular, such as
Electro. What that say?
some of elementary steps. Unimolecular, it's usually a decomposition reaction where it's just one reactant just kind of decomposing on itself, just like meh. Okay, kind of like what will happen at the end when we all like get through the AP exam. We'll start decomposing ourselves and just like giving up. Although actually post AP exam, I have some fun things planned for you guys, and I have some hopefully guests coming that should be pretty cool.
Neil deGrasse Tyson?
No. And if you have collision of two species, we call that bimolecular reaction. And if you have a reaction of three species, it's called termolecular, which by the way, would like never happen because the whole point is to not be termolecular. It's like avoid that. But you know. Okay, so quick note on reaction intermediates. Okay, these compounds, or species, maybe I should just say species, produced and then consumed. Between elementary steps. They're kind of low-key, like a theory that we kind of made up in chem, but they were proven to be true enough. So it's like, have you ever seen an intermediate? Well, have you ever seen an atom? Well, but all the data says, yeah, they're real. So are they real? Sure. Real enough. And that's the end. Oh, yes. Right, because remember, catalysts are consumed then reproduced. Intermediates are produced and then consumed. It's the flip.
So it's kind of like what were we calling it? When they get matched into each other.
Collide.
Instead of an activation complex, you have completely new.
A new
molecule.
temporary. That's where the temporary covalent catalysts come into place. The similar idea. You get this you get this temporary actual compound that forms whose bonds for whatever region arrangement, it's easier to break, allowing the next particle to come in and form the desired bonds.
But we've never seen what molecule they
I mean, like technically, no, we have programs that can graph it quite accurately with all the relative energies. And we're like, yeah, that's true enough. It's logical. It makes sense with everything that we know,
we don't know
but we don't ever see them.
So
But you've never seen an atom, so what are we doing here?
I mean, I see some right now.
No, you really actually don't. You don't truly see an atom. You see the macro compilation of them, but you've never truly seen an atom. And by the way, the quantum mechanical model is not the end. Molecular orbit theory tells me that an atom is actually wave energy. That's it. So you are seeing wave energy become matter at a macro scale. You have never seen an atom.
But we
I saw
we
that.
have ways of like taking a very good microscope and looking at atoms, like being able to.
Yeah, I've
play
seen
with
that
atoms.
video where they make the atoms dance.
Well, what? Oh, you mean when they like?
It's like
Oh, because when you stretch bonds, atoms can twerk. When you stretch bonds, they can move in and out. They can move side to side. They can shimmy and they can twerk.
It's like, have you not seen that stop motion video? Where it's like they make.
Have I
a
not
video
seen
with
it?
Atoms. which
Sounds
is,
like I
a
have
little
not.
Ball, but every it's made of.
But see, that's the computer generated thing, right?
No, it's actual
They
atoms.
took photos of atoms.
Wow. Have I not up to date?
They
Maybe.
did this like 10 years ago.
I was still in college 10 years ago. I was in high school and in college. My professor said there's still none, and I feel like there would have been a bigger deal made out of this. I still hold by my stand. Anyway, that was a lot of extra, guys.